So now that we have our two functions here, let's apply them to a scenario more akin to something you would see in real life. So here's a pipe network. And so this pipe network is made up of a series of nodes. So this is node 0, node 1, node 2, and so on. Well, not really so on. There's only those nodes. And then also you could assume that there is a fourth node down here. I'll explain that in a second. So in between these nodes, you have a series of pipes connecting these nodes, right? And these pipes all have associated measurements with respect to their geometry, right? Their length, a value for k. Maybe there's a T joint or something in there, and then also the diameter of the pipe. And for the sake of this problem, we'll assume that these pipes all have the same roughness as well. So you can see that these nodes also have values associated with them, right? So they all have an associated pressure and height, and this fourth node here that really isn't drawn, but these pipes coming out of node 1 and node 2 going to what looks like nowhere, you could say that those are going to the environment, okay? And the environment you could describe as a fourth node, a node 4. So looking at this problem, initially the first approach we're going to take is we're going to say that we have good guesses for the z value associated with node 0, and also a good guess for the k of this pipe that's going from node 1 to the environment, or node 3, you could say, right? So with those assumptions, we're going to basically take all the information we have here, and using our functions that we wrote in part 1, we're going to solve for all the differential heads and flows through all of these pipe segments. Okay? So assuming that's the information we have about our piping network, if we want to use our functions to find the associated delta head and flows to this piping network, there's going to be a challenge here in that we don't know the delta head or the flow, right? We might know the flow going to the environment, but we don't know anything about the flow or delta head between really any pipe that's associated with these internal nodes here. Node 1 and 2 are the internal nodes of our system, where node 0 would be the source of the flow in our system, and the environment, or node 3, would be the sink of our system. So we're going to have to utilize the functions that we've written in part 1 and somehow make guesses for the pressure associated with the internal nodes, because once we make a guess for the pressure, we're going to be able to calculate the heads at those internal nodes, and in turn we'll also be able to find the delta head of the pipes. So first, let's get started with I'm going to make a pipe array that contains pretty much all of the known measurements associated with our piping network. So let's do that. And let's make a comment here to make this a little easier to comprehend, so we don't make any mistakes later on. So this is like our pipes information array. So let's make an array And let's start putting some information from our pipe. So before I start typing in some numbers, yeah, let's kind of decide how the order we want to do this. So so this is information associated with the pipe. So the first thing we probably want to know is which pipe are we talking about. So let's define a node in and a node out. So let's start with a node out and a node in. So for example, for our pipe segment 0 to 1, we would say 0, 1, right? Because we're going out of node 0 and going into node 1. Okay. So then, what is the other information associated with that pipe between node 0 and 1? Well, we have a K value, a length, a diameter. So we have a K value, a length, a diameter, and also an associated roughness with that pipe, surface roughness. So if we're looking at that K value is 1, the length is 20, the diameter is 0.1, and our ED is going to be 0.001. And I'm going to say that the 0.001 will be the ED for every single pipe. So let's double check to make sure I enter that in correctly, and then we'll go ahead and do that for the rest of the pipes in our system. So we have node out, node in. So we're going out of 0 into 1. That K value is 1. That length is 20. The diameter is 0.1. And I forgot a comma there. And then associated roughness. Okay. So that's for our pipe node 0 to node 1. The next one we can do is 0 to 2. So then that K value is 1. That length is 30. That diameter is 0.01. And our epsilon over D is the same. So let's make our next pipe. Let's say we did 0 to 1, 0 to 2. Let's do 1 to 2. 1 to 2, that length is 5 meters. Oh, that's not the right order. We got to do K, L, D. So 1, 5, 0.01. And then the associated roughness, 0.001. And then, so that was node 1 to 2. Now let's do node 1 to 3. I'm going to use the number 3 to refer to our, our environment. That's our sink node. So if we're doing 1 to 3, we're going out of node 1 and into node 3. And then the K value for that, we said we're going to assume that that is 6. The length is 0.1 meters, the diameter is 0.01 meters, and of course the same roughness. So that was 1 to 3. So we've done all of our pipes now, except for the final one, which will be node 2. We're going out of node 2 into our environment, node 3, and that K value is 1. The length is 0.1, the diameter is 0.01, and then our roughness. So I'm going to pause here and just double check real quick that this array is set up properly. It looks like I already missed a bracket there. Okay, so that looks good to me. Let's double check to make sure I didn't. Okay. Let's see. Okay. So that looks good. So the first thing I'll probably want to do is, you know, maybe since all of this array has a number of pipes, right? Let's give a number of pipes. So let's do n pipes equals let's see, we can get the dimensions of pipes, right? And that'll give us that. And we're interested in the number of rows. So I can do pipes dot shape of 0. And I should get a 5 out of that. Good. Okay. The other thing I might want to do is the number of nodes, right? So we should have 4 nodes, but let's make this a little generic. And let's say, can I do this? Pipes.max? Okay. So let's look at all of the rows associated with the node n column, which is going to be column 2, right? Because our node out, you know, the sink, our final node 3, you know, nothing will be coming out of it. So naturally the biggest node will be contained in this column, and Python indexes at 0, so it actually should be like that. And maybe I can't do that. Oh, right. Referring to positions here. And then I should add 1. No, oops, shouldn't be bracket there. Right? I'm skipping things. Let's just type this out the long way, right? So I want np max. I'm going to look at pipes, and I want to look at all the rows of the second column, which is 1, and I want to add 1 to it. Man, I really keep doing that. Right? That should work. Okay. So let's see, n nodes is 4, right? That is a floating point, though. If I'm with a number of nodes, it probably would be a good practice to make that an integer. So add as type. So now we should just get an integer, right? Yeah, 4. And is that right? That is correct. Cool. Okay, so the other thing I probably want to do is I want to make a series of arrays that are, you know, basically taking all these columns. And, you know, for example, we can say node out, and we're going to take the first column here, and you know, as before, we want this to be an integer. np dot, right, and then we should get the first column there in our pipes array, so we should get a 0, 0, 1, 1, 2. An array of integers, right? Because okay. So then similarly, let's do the same exact thing, and in fact I'm just going to copy and paste this. want the first column now. We also want that as integers. Let's double check that. Oops. I want that. 1, 2, 2, 3, 3. Yep. Okay, and then next we probably want our k values. And this will be our 0, 1, 2, I believe. Right, and we actually don't want that to be an integer, right? Well, I guess k values could possibly, but I'm not going to worry about that. I'm just going to leave it as floating point. And then, okay, let's do our lengths. I'm just going to type this out, lengths. So that would be mp.array. Right, and then we just want the succeeding column. Let's just check again, just to be absolutely sure we're doing that right. Yep. Okay. So, and then we'll do our pipe diameters. Let's just call those diameters. And pipes. And the next one is 4. And then they're all the same, but let's, yeah, we should do that anyway. Should store those all in an array. What is that? It should be 5. Okay, that worked out. So if we look at our picture, we also have some values associated with the nodes themselves, right? So this little section here is kind of information associated with the pipes. Really more just this part, but let's do the same thing for our nodes. So in this case, let's go ahead and make a Z array. And you know, assuming the positions in this array, you know, they're going 0, 1, 2, 3. Let's put the associated Z value, pairing that with its position in the vector. So this 0th position, we're going to put 15 meters because that's what we assumed that would be, right? And then for the first position, that would be a 0. Second position, second node should be a 0. And our third position, we'll also assume that its pressure will be 0, you know, like a gauge pressure. And also with that environment, we'll assume that the Z equals 0. Or sorry, well, I'm getting backwards here because we're going to be making 2 arrays here, right? So do I want to call this P? Yeah, that's probably okay. So every pressure, I don't know the internal pressures, but I know I should have an array with 4 positions associating with our 4 nodes. So let's go ahead and just make an array of zeros, and we want that to be the length of the number of our nodes, right? So if I print P here, right, we have our 4 zeros, and if I print Z, right, the only node that isn't at a height of 0 is the first node, the 0th node, really. So that looks good. So maybe the next thing then to consider is, right, you know, our pressures, we didn't know all of our pressures, so maybe let's initialize some arrays for the things we don't know. For example, we don't know the flows, and the flows will be associated with pipes, so let's for now make an array of zeros with length of the number of pipes. Right, so if I do flows, 1, 2, 3, 4, 5. And how many pipes do we have? 1, 2, 3, 4, 5, right? Okay, and we also do not know, what else do we not know? We also do not know the heads. The heads, well, we don't know the differential head, basically because we don't know the heads at all of the nodes, right? We don't know the heads at the internal nodes specifically, right? because at our node 0 and node 3, those are our source and sink, we know the associated pressures and heights. So we do know the heads there. So first let's make an array of zeros, and we'll put in those heads for our known heads in a second here. So there should be a length of the nodes, and so what are our heads? I'm not sure if I want to be doing that with the heads yet, because as I said earlier, we don't know the internal pressures of our system. So at some point, we're going to be using those pressures and heights to calculate the head, and I don't want to be worrying about different ways of calculating that, because there's some zeros, and I don't want to have to worry about, well, I'm not going to worry about it for now, but we are going to have to take care of that later. Also, these flows, we do know the flows going to our node 3, our environment. So which pipes are those associated with? Let's go up to our array here. We know 1 to 3, so this is 0, 1, 2, 3. So at position 3, our flow is 5 times 10 to the negative 4th meters cubed per second. And then subsequently we also know 2 to 3. 2 to 3 is 0, 1, 2, 3, 4. Yeah. So we also know that, and that is 2.5 e to the negative 4. Let's double check to make sure I did that correctly after this cell runs. Okay, let's double check what this looks like. Okay, that looks right. Yeah, that looks okay. Okay, so we're at a pretty good starting point, I think. The approach we want to take now is, if we go back to our picture, our pipe network, what are we trying to do again? We're trying to find the differential heads and flow rates of the pipes in this network. So, if we're looking at this, it might look like we really don't have anywhere to start, but we are, I believe, for the, we know a lot of information about these nodes, right? In particular, we know the heads of the external nodes, right? It's the internal nodes where there's a problem. We don't know the pressures. Now, let's say we know those pressures. If we know those pressures at the internal nodes, we'll know the heads at those nodes, and in turn, we'll know the differential head for every single pipe in our network. And what do we do in part 1? We used a function to find the flow rate when given a known delta head. So, we need to make some kind of guess for the pressure. So maybe something we can do is take the average of the external pressures, right? So our pressures, unfortunately, if I print those out real quick, the external pressures we know are 0, right? We know the external pressures are 0. It's these internals that truly aren't 0. But how can we make a guess then? Well, this is probably where calculating the external heads is going to be useful. So maybe we should do something like that. So we could say well, if we're going to explore this, this comparison between external and internal, heads, we probably should describe the indices associated with those, right? So that'll make placing values inside of our heads array, for example, or perhaps our pressure array a little bit easier and less prone to mistakes. So let's start with maybe external node indices. Well, we know, we're going to make an array here, and we're going to want to make these integers, but for now, we know that for an external node, certainly 0 is always going to be a 0, right? And then probably, how should we approach maybe the external node? Well, maybe we can do something similar as what we did in for our nodes, right? So maybe let's see here. Yeah, we were looking at this same column. Actually, I can just take this out the +1 because we're interested in the indice this time. And let's see what happens. Not subscriptable. I don't have parentheses. Sweet, let's see what happens. 0 and 3. And as with before, we want these to be integers. So let's do that. Perfect. So 0 and 3 are our external node indices. And let's do something similar for our internal node indices. Let's name that similarly. Yeah, so in this case, we can we know our external node indices, so really we can chop off those those outside positions of our range of nodes. So arrange n nodes, and we want this to be a set. And we want to subtract off the set of our external node indices. Awesome. Okay. Is that right? Let's see what happens. We got 1 and 2. We want to make this a list. I might have to clean this up. I kind of was a little sloppy the way I typed that. Oh, okay. All right, that's good though. So it works. And if you wanted to use a different piping network, you get to the correct result. Okay, so now that that's done, let's go back to our kind of heads situation, right? Okay, so now looking back at this heads situation, since we don't know the pressures at our internal nodes, as we were saying, we might have the idea that those internal pressures would be the average of the external node pressures. But we're getting kind of tripped up here because we don't know what, well, we actually do know those pressures, but they're 0, right? So that's not going to help us. But we do know the heads at the external nodes. And if we know the heads of the external nodes, we can take the average of those. Those will be non-zero values, right? Of course there's going to be a head associated with them. So maybe if we take those averages and say that the average of the external heads is the head at each of the internal nodes, we know the heights at nodes 1 and 2. And therefore we will have an associated pressure, and that can be our guess for our pressure, right? So that was kind of a mouthful. Let's start somewhere. Let's start with right. We want to find our external head average. So external head average. So how can we do this? Well, we know our pressure over rho g plus z equals h. So we have to take the pressure at our external node indices. This is where that's going to come into use. So the pressure at our external node indices, and this will actually be 0 anyway. You know, the actual calculation, these pressures are 0, but that's all right. The external node indices divided by rho divided by g. Yeah, I still got those up there. Okay, and then that is going to be plus the heights at my external node indices. And I want to take the average. So MP dot average, or I probably want to do it like that. Only integer scalar arrays can be converted to a scalar index. Maybe we'll check these again. Comment this out. Integer. Hopefully these aren't integers. Okay. That is not the, that's not, no, I don't want that at all. I don't know why I did that. No, this can't be an integer. This should work now. No. Arrays uses indices must be of integer or Boolean type. What happens if I just type P? Okay, so there's a problem with external node indices. What if I just said 0, 4, 3? Oh, I can't do that. No. Yeah, I don't know what I'm doing here. Let's see. No, I need to redo this. Get rid of all that. Let's use an axis. Dot max. That's going to say 0, and I want 1. Position that. This needs to be an integer. Error. Invalid syntax. Maybe I didn't need that. Oh my God, that's what I did wrong. That should not be there. Okay. There we go. All right, finally. Um, I really think this should work now. No. I'm going to pause here for a second because I'm really having trouble seeing what's wrong with this. Okay, so it's a good thing I put a break in there because I just spent a solid 10 minutes troubleshooting this. So basically did some reading on data structures in Python, and it's pretty obvious now. You can see the error it gave me. Right, saying list indices must be integers or slices, not list. Well, I was trying to do mathematical operations on a list, right? Because my z here is a list right now when it needs to be an array. Forgot those parentheses. Right, perfect. So, okay. So now we have our external head average. And what did we say? We said that we were saying that our guess for the internal pressure arises from the assumption that the average external head is equal to the internal head, right? And because we know the heights of our internal nodes, we can solve for the pressure at the internal nodes using this this assumed external head average being the internal head. So since we know that, let's call this an internal head guess, right? And we know, like I printed down here earlier, the external head average is 7.5, right? So let's, how is it, fill or full? Okay, so we're going to fill an array that is made up of, that's our shape, our internal node indices, and we want to fill it up with our external head average. So then if I print that, right, so now I have an array that contains the external head average. So now we need to find the internal pressure as a result of this internal head guess. So let's go ahead and call this an internal P guess, I guess. That's probably fine. Okay, so that means that we have, solving for the pressure, we'll have our internal head guess, right, at, well, there's only two positions there. We don't need to worry about that, actually. And then we're going to subtract the heights at the internal node indices, right? And then that's going to be multiplied by rho and g. Okay, let's see what we get. Did I do that correctly? Okay, interesting. So now we have our internal pressure guesses for our internal nodes, and that's something like 74,000 pascals or something like that. Right, so that's it's something like that, and that's a pretty decent internal pressure guess, right? So now we have our internal pressure guess. The next logical step would be to say that, okay, if we have our internal pressure guess now, we can make a guess for the right. We also have like an internal head guess, right? We said that was the average. And the function earlier, of course, we wrote a function that will give us the flow with from a known delta head. So the next step we probably want to do is find the delta head. So finding that delta head is going to allow us to find the flow. And in order to find that flow, if we go back to our function here, there's some guesswork involved, right? And our delta head in itself is also a guess, right? And that arose from the assumption that these values are our internal pressures. So we're again we're going to need to use a root finding function, and in this case, I think we'll be able to use Newton. Possibly, might have to check that out later. But this first function, the process of finding these roots is going to rely on the fact that this pipe network, we're going to assume that it is steady state, right? And with that assumption comes the fact that the net flow through the internal nodes is going to have to be equal to 0, right? So from that, we're going to be able to make a function here, and let's call it something like that. What did I use earlier? Flow adjust to 0. Let's do QNet adjust to 0. And we are going to have to supply an internal pressure. So this internal pressure is what our root finding function is going to be incrementing and adjusting until the equation is satisfied. So the first thing we're going to want to do is when you supply, when we use this function and supply an internal pressure, we're going to want to say that P at our internal node indices is going to be equal to our internal pressure, right? So whatever the supplied internal pressure is, which in our case is going to be a guess, those values are going to be assigned to our pressure array at the locations of the internal nodes. Okay, so then moving forward, right, we're still interested in we're going to have to end up using this flow function, right? We need to know a delta head. So let's keep moving towards that. What is our delta head here? Well, heads is our heads array, which is over here. And in fact, that's a good reminder. I need to state that this is a global variable. Heads. So our heads, we need to calculate those, because right now, using this function, our heads are all 0. So heads are a head at a node equals, right, our pressure. So good, we already have our pressure array divided by rho divided by G plus Z. And now our heads array, which is the same, which has the same dimensions of our pressure and height arrays, we're now going to have our array for heads. So that's perfect. Now we know all the heads in our pipe network, and we can move on to calculate the delta head of every single pipe segment. So in order to do that, in our original function, right, this was just based on a single pipe segment, right? And in our case, we're going to have an array. We're going to have multiple pipe segments. So let's utilize a loop, right? So in range. Okay. So we're going to want to go through how many times? Well, the differential heads are associated with the number of our pipes, right? So now we're going to go through this loop, and I forgot a colon. So we have to calculate our delta head. What do we call that? So I don't want to call it del head. I'll call it D head. So D head. And we're going to have to take, at every node, we're going to have to take the difference in head between each of the nodes, in our pipe array. So how can we approach that, right? We're going to be using our heads array, right? And we want to be taking, so let's think about this for a second. I is going in the range of the number of our pipes, right? And the number of our pipes are associated, right, with each of these rows, right? So if our I is going to be incrementing through that, for example, when I is 0, we're going to be starting here. So we want the head at the 2 node, or sorry, the head at node out, right, and subtracting that. We're going to be taking the difference between these. So really, it should be the node in, the head at the node in minus the head at the node out. So let's do that. So let's take the head at the node in at position I, and then subtract the heads at the node going out at position I. Okay, so then from there, if we know our delta head now, well, this is going to be incrementing through, right? So each time this delta head is going to be changing. So within this loop, we're going to want to use this delta head before it gets written over. So while we know the delta head, remember when we know the delta head, we can utilize this function. So before this delta head gets overwritten, right, from this iterating loop, let's go ahead and assign to a position in our flows array. Let's go ahead and assign the flow. So we have, while this is going through, we have our D head, and then our K at that associated position, the L at that associated position, and our epsilon over D at that associated position. So now what's happening is every time we're going through this loop, for example, again, if we're saying, maybe in this case, let's say I is 1, right? So if I is 1, we're going to be looking at this pipe, right? So we're going to look at the head at node 2 and subtract from that the head at node 0, right? That's going to be our delta head now. We have our delta head. So now we're going to move on, and in our flows array at position 1, we are going to place the output of our flow function at our given delta head, which this was found at position 1, right? Our 1 pipe in our pipes array, and it's going to use all the associated K, L, epsilon D, right, for that position 1, and it's going to store it in our flows array. So then now that we know the array with our flows in it, what is going to be the next step here? This is where we're going to have to use the idea of our net flow, our internal net flow, being equal to 0, right? So did we define net Q? No. I'm going to go ahead and initialize that. Shouldn't really matter where I put it. So let's call it net Q equals MP0s, and it should be the dimension of our internal nodes, the number of our internal nodes. We probably want to make that generic. So let's come back to this. And let's say something like the number of nodes internal, something like that. And that should be the length of our internal node indices, right? Because there's two positions there, right? So we should have, in our case, there should be 2 internal nodes, and that should be right. Let's double check that. So n nodes internal. 2, perfect. So now that we know that, let's just initialize a net queue, and let's not make the same mistake I made earlier and make this a list. This needs to be an array, and it should be no, that's I'm not sure about that. Let me think about this for a second here. So we're interested in this net flow or net queue. Yeah, I think this should just be the number of nodes, right? So net queue. Oh, that's not right. This needs to be zeros. Yeah, I think we do want to do it this way because, right? We know our flows. We know the flows through every single pipe segment. So, I'm going to go ahead and stick with this. I think because when we're using our root solver, we'll tell it only to zero out the internal indices of this, and there won't be any the flow coming out of node 0, for instance, is that's just what it is, and the same with what's going into node 3 here to the environment, right? So let's move forward with this. Okay, so now if I initialize netQ outside of this function, I have to also add that here. I think that I need to think about all the global variables here. Heads and pressure are also both referred to outside of this function, so we are going to have to add that as well, I believe, just to be on the safe side. Yeah, no, I am going to have to. Right. Maybe not pressure, but just to be on the safe side. Okay, so we have our QNet here now, and we have our flows, and our QNet is made up of zeros. So the first thing let's do is get our net Q here. Let's put it here. So we're going to use something called numpy.add@. And looking at this, we're going to choose our array that we want to be making changes to, which is going to be netQ. So if we're thinking about, we have the flows associated with every pipe. We know the flows that are going to a node, and the flows that are going in a node, and the flows that are going out of a node, right? So if we add all of the flows going into a node, our flows array is now going to have that flow associated to it in our net Q array. And then to then properly reflect the net Q, we will also have to subtract the flows going out of that node. So if we're adding, we want to add the nodes that are going in right now. So then let's say at these positions at node N, let's go ahead and let's add the flows. Right, so at the indices associated with node N, we will be adding flows. Okay, I think that should work out. Right, so you know, at the values in here for node N, that's going to place that associated flow at that position into our net Q at that associated node. So now we've added the flows going into a node. In order to get the net, we're now going to have to take off the flows leaving that node. So let's use np.subtract at, and the same array we're looking at net Q, but this time we want to be subtracting the flows going out of the node. Okay. All right. Okay, so let's do some testing here because I just typed out that whole thing. Let's say return flows. Okay. So let's go ahead now and use our function, and we want to supply the internal pressure of our function as our internal pressure guess. I got an error. int object is not subscriptable. Oh, I forgot. Oh, what happened there? I'm just going to retype this just so I get the, you know, this to show up for me. Okay, so we have our D head, K, position I, L at position I, What is going on? It just skipped D. That's really weird. I'm entering that correctly, right? I'm going to double check this. Flow. Right, flow after my delta head I have KLDED. And I have KLDED. That's super weird. No, I'm still wrong. INT object is not subscriptable. I'm going to retype this whole thing because I feel like I'm doing something wrong with my syntax. Flow, right? That should be D head. And now I should have my K. And now my L. Please. Oh, I did it again. Why is it doing that? Oh, I think I know why. Okay, I'm making a mistake here. Okay. Let's make sure we're doing this right now. My L is called lengths, right? Lengths. Oh man, I did that again. Hopefully this shouldn't be a problem. Diameters and then ED of I. That's what I called it, I think. Let me double check that. ED. Okay, was it lowercase? Okay. Oof. Okay. Oh, okay. I'm really not sure why it was it was kind of skipping over that highlighted part for D. Okay, so these are our flows. These are our flows now. Okay, so that's printing out. Let's get the delta head this time. Well, that's not going to do anything for us, really. It does. I think that's right, though. Right? Yeah. Yeah, the first one should be. Yeah, it should be -7.5, but that doesn't matter that much. Okay, let's print those flows again. Okay. Okay, so actually, I think this is good. This is looking good because 0, 1, 2. So at position 2 on our pipes, 0, 1, 2. Right, if we look at our picture, over in this corner again, from 1 to 2, right, according to our guess, we haven't done any, we haven't solved any roots yet, right? The heads at nodes 1 and 2 right now are exactly the same because the internal pressures, that were assigned from our guess are exactly the same. So we have the same pressures at nodes 1 and 2 and the same heights at nodes 1 and 2, which means there's no delta head. The delta head is 0, right? So judging on that, I think we're looking good right now. And yeah, I think that's a good sign. I want to try out now using our solver. So if we want to use, here, I need to read about Newton here for a second. Can this use arrays? Newton returns an array, and function must be vectorized and return a sequence or array of the same shape as argument. I think there's a different function. I can't remember off the top of my head. I'm going to pause here for a second and look that up. Okay, so there is a function in SciPy, and it is called root. So just to look at root here, this is what we're interested in, right? Because in our case, we are finding the roots of there's an array here, right? We're finding the roots with all these values in our array. So find the root of a vector function. Okay, so in our case, we want to find the roots. So what is our function here is qnet adjust to 0. And what are we incrementing? We want to increment internal p, right? Because we're supplying internal p. We're saying that we're supplying it with a guess. So that is our initial guess. Okay. And let's just call this result. And just go ahead and do that. Internal p is not defined. I guess I have to make internal p global. Or I have to initialize it, and that's probably that's probably what I want to be doing here. So let's go up here, put it next to this, and we'll say internal p equals, right, initially it's fine if it's zeros, and what does the size of this going to be? Oh, this is where, did I keep that? End nodes internal. Okay, let's see. Think about that. I think that should work. So now we have an array. These are zeros. And that's fine. Yeah. So, okay, let's see what happens. Fsolve, there's a mismatch between the input and output shape. Input and output shape of the function argument. Yeah. Oh, well, so we're supplying this root function with the output of this function. We just threw the flows at it. That's not what we want. The internal net Q to be 0. So we need to return and give to this root function. We want to return net Q at the internal, internal node indices, right? So let's see if that does the trick. Okay, it didn't fail. The iteration is not making good progress. Improvement from the last 10 iterations. Success false. Okay, so it failed. It failed. So what went wrong? So this root function is using the output of this function, netQ. So then it gets this return from netQ, and it's obviously wrong. So it's going back and adjusting internal pressure and going through this again. And it's accumulating. Okay, so our netQ needs to be changed before we add on these flows again. So we need to say is it like fill with a scalar value? Okay, so we want to fill that with zeros, right? Because it's accumulating all these net Qs. You know, without this here, you know, if I comment that out, it's going into, this is where problems are really arising. It's np.add and subtract that, because the first time, you know, it's going through this function, netQ is an array of zeros, but then subsequently each time, you know, and you can see, you know, when it was trying, it wasn't making good progress. Last 10 iterations, it was going through it 10 times, and the netQ was different each time going into this function. So hopefully I should take care of that problem. Yes, okay. It says the solution converged. Now, does this look all right? Okay, so now it's saying the results, these are what our internal pressures look like they should be. Okay. I want to print let's just print the flows as well. I'm curious. Okay. Okay. So then these are our pressures for our internal nodes, right? For node 1 and node 2. Let's print the net flow. I'm just curious to see what that looks like. Okay. Cool. So these are obviously pretty much going down to 0. Okay. Okay, so I actually realized that I made a mistake here using my root function, because when the function was asking for my initial guess to use, I said internal p, and that's not what I want to supply this function with. I wanted to supply it with my internal pressure guess. So funnily enough, they seem to converge to the same point. You know, if you look at these numbers, you know, after I make the change here for my internal pressure guess, two things change. First of all, the output right here, this row right here is the net Q for the internal node indices, and I'll get rid of this for clarity's sake. And this row right here with the X is your internal pressures. So if I go ahead and run this now with the internal pressure guess, the first thing I noticed is it converges, and the net flows are much closer to zero. Right before I ran this, it was e to the negative 10 for both of these. Now it's e to the negative 12, e to the negative 17. And they're, you know, it's pretty much, it converged to the same value. So I guess that was a lucky break initially, but that's, you know, definitely the intention was to use this guess. You know, maybe in another pipe network, you wouldn't have been as lucky. So, yeah, so now we know our internal pressures, and therefore we know the true delta heads and flows through our network. So I went ahead and formatted these results, so it's you know, we have a nice little picture of what the true values for a pipe network are, and I wasn't really as familiar with how to do this off the top of my head, so I didn't want to drag things on any longer than they already have been. So, so yeah, in conclusion, you know, our internal pressure guess, it really all started with that. You can see that these we have our true internal pressures now, right? We also have the net flows through each of our nodes. As expected, the net flow through the internal nodes is 0 because we have a steady state pipe network, and we have all of the flows through the pipe segments in our pipe network. So yeah, thanks for watching.